So this is the second question related to half-wave rectifier circuit which we'll discuss. So here it is given an AC supply of 230 volt is applied to a half-wave rectifier circuit through a transformer of turns ratio 10:1, and it has been asked to find the output DC voltage and the peak inverse voltage, and it has been given to assume that the diode which is used is ideal, that is no forward resistance, no voltage drop that is cut in voltage, nothing like that. So let us draw the circuit here. So here we have an AC supply voltage of RMS value 230 volt, and we have a step down transformer which is used. Okay, then we have an ideal diode connected, and then we have a load resistance. The diode is ideal, which means no forward resistance. Here the turns ratio is 10:1. Okay, this is the circuit. Now here, this is the primary winding, this is the secondary winding. Here turns ratio means number of turns of primary winding to number of turns of secondary winding is equal to 10/1. Okay, now here we have at the primary side the RMS value of the voltage is equal to 230 volt, which is sinusoidal, okay, AC. So the maximum value of the voltage at the primary side will be, we know, Vrms is equal to Vm by root 2. Here you don't be confused that why here it is root 2. For half-wave rectifier it should be Vm by 2. But see here we are discussing only about the primary side which is connected to the input supply. The input supply is sinusoidal AC. For sine wave, the RMS value of voltage or current is equal to Xm by root 2, that is maximum value or peak value divided by root 2. So here it would be Vp max, it would be Vm by root 2. So the maximum value will be equal to Vp RMS into root 2 here, or it will go to the numerator side. So this is basically equal to 230, which is here the maximum value or the RMS value of the primary winding voltage which is connected 230 volt. This is always the RMS value. Always remember, when it is given 230 volt, directly it is given that it is connected to an AC supply of 230 volt or any value, it is always the RMS value, root mean square value. So here it is Vp RMS into root 2, RMS value of the primary winding voltage into root 2, which is equal to 230 into root 2. That is equal to 325.3 volt. Okay, that is the maximum value of the primary winding voltage. Now the relationship between voltage and turns ratio, that is given as Vp by Vs is equal to NP by NS. Here the subscript P and S stands for primary and secondary windings. The voltage across the primary winding will Vp divided by the voltage across the secondary winding Vs is equal to the number of turns of primary winding divided by the number of turns of secondary winding. So same can be done for Vp max by Vs max. We are interested in finding out Vs max. So Vs max is equal to Vp max into Ns by Np. So which is equal to, we have calculated Vp max here 325.3 into Ns by Np, which is 1 by 10. That is equal to 32.53 volt. So this much maximum value appears across the secondary winding here. This is the maximum value of the voltage which appears across the secondary winding, which is lesser than that of the primary winding. Okay, this is important here. Vs max, the maximum value of the secondary winding voltage, is equal to 32.53 volt. This is important. Okay, this. Now, the question that is asked here is to find out the output DC voltage. Okay, the output DC voltage. Now here you see there is no forward resistance of the diode. The diode is also ideal. There is no cut-in voltage, no voltage drop. So the voltage, the maximum value of the voltage which will appear at the output at RL, that will also be equal to this much, 32.53 volt. Okay, and we know the output is DC, VDC, the output, and the DC output or any average value or DC value is given by Vs max by pi. Okay, if you remember, DC value is also called as average value, that is given by X max by pi. Okay, this is the average value or DC value, and AC value, which is also called as RMS value, that is given by X max by 2. This is for half wave rectifier circuits. Here we can only do directly for voltage because there is no forward resistance. Zero forward resistance, the diode is ideal. That's why we can use this equation related to voltage. If it would have been not given that the diode is ideal, then we have to find the current, and then we have to do the IDC value is equal to Im by pi. That we have to do. Okay, so this is the VDC output, which is Vs max by pi, which is equal to 32.53 by pi, and that is equal to, if we calculate, it is coming around 10.36 volt. Okay, this is the VDC output, which is equal to IDC into RL, this, or Im by pi into RL. Same thing, same result you will get. Okay, then it has been given to find the peak inverse voltage. So the basic definition of peak inverse voltage is that it is the maximum value of the reverse voltage which appears across the diode. Okay, so here we found out that the maximum value of the secondary winding voltage is 32.53. Vp max, we found out it is 325.3 volt. So the across the primary winding, the nature of the sinusoidal AC value is like this, with peak value, maximum value 325.3. This is plus, here it is minus 325.3. This is the primary winding. When it is passed through the transformer, it is converted to like this. Here it is plus 32.53, here it is minus 32.53. The voltage is lowered, it's dropped. So this is the maximum value of the voltage in the negative direction, minus 32.53. This is across the primary winding, this is across the secondary winding after it is passed through the transformer. So the peak inverse voltage, which is the maximum value of the reverse voltage which appears across the diode, is minus 32.53 volt, or negative of the maximum value of the secondary winding voltage. This, okay, this negative of the maximum value of the secondary winding voltage, which is 32.53 volt. So the first question, the output DC voltage is here VDC Vs max by pi, which is 32.53 divided by pi, which is 10.36 volt, this much, and the peak inverse voltage is equal to negative of the maximum value of the secondary winding voltage. Okay, this.